Yes, I did. Hello students, in this video we will discuss some concept from the chapter non-metals. Okay, let's start. In this video we will learn about the allotropes of carbon. Specifically, we will learn what an allotrope is and have a look at the different allotropes the element carbon can exist as. We will investigate their structures and how this influences their physical properties. Lastly, we will discuss the uses of these allotropes. Okay, let's begin. Just look at these pictures. It's a pencil and a diamond. Did you know that the gray tips of pencils and shiny colorless diamonds that we saw in these pictures are both composed of same element? Yes, this element is carbon. The tip of a pencil and diamond are two different forms of the same element carbon. We call these substances allotropes of carbon. And just look at what is an allotrope and why these two objects or these two things are composed from same element. Just discuss. Okay, what is an allotrope? Allotrope is defined as the different forms of the same element having different physical properties are known as allotropes, and this phenomenon is called allotropism. Okay. Allotrope is something that one of the different forms of the same element. In other words, some elements can exist in various forms. Not all elements can form allotropes, but only some of elements in group 3 to 16 they have some allotropes. Just leave. It's an important thing to remember that allotrope is not a compound. Okay, allotrope is not a compound. Allotropes refers to compound. Allotropes refers to the same element existing in different forms, while compound refers to the different elements bonded together. We know that what is an element, what is compound, and we studied these topics in earlier classes. So just look that allotrope is not a compound. Allotrope and compounds are different concepts. And we discuss allotropes of carbon. There are allotropes of carbon categorized into two. They are crystalline allotropes and amorphous allotropes. Then crystalline allotropes. In this video, we just discuss only about the crystalline allotropes. In later videos, we will discuss amorphous allotropes. Okay. Now, the crystalline allotropes. We know the crystalline allotropes are what we will be focusing on this lesson. We will have a look at the diamond graphene structures and fullerenes. Okay, there are some. What are the crystalline structures of diamond? Graphite, diamond, fullerenes, graphene. And in this video, we discussed these crystalline allotropes, their properties, their uses, and etc. Let's start with diamond. Okay. The diamond that we know from the jewelries are cut in a way that they are to maximize the amount of light refracted from the sea to make them look like sparkly and pretty. But there is much more to diamond that use in jewelries. Imagine if we could zoom in this structure. Okay. Just zoom and we got its molecular structure. Okay. Of course, a magnifying glass wouldn't work. We had need a electron microscope. We had see the following internal arrangement of atom. Diamond is a network covalent structure, otherwise known as a chain covalent structure. What is the structure of diamond? In diamond, each carbon atom is covalently bonded to 4 other carbon atoms. This strong bond is responsible for the hardness of diamond. Due to the absence of free electrons, diamond does not conduct electricity. In this structure, we clearly see that there is no free electrons. All the carbon atoms are bonded together to 4 other carbon atoms. So, we conclude that diamond does not conduct electricity. What are the properties of diamond? Its strong bond. Due to its strong bond, it is very hard, do not conduct electricity, high thermal conductivity, high refractive index. These are. And because of this, almost carbon atoms are network covalent structure, could be considered as a central carbon atom. It's a bit for those, the edges each their own tetrahedral array, something like that. This structure gives diamond a specific properties and related uses. So just look at once again these properties: hardness, do not conduct electricity, high thermal conductivity, and high refractive index. Okay, the second crystalline allotrope is graphene. Let's start with graphene. The shiny tip of the pencil. Okay. Unlike diamond, in graphene, each carbon atom is covalently bonded, not to 4 but 3 other carbon atoms. Just look. If you take this carbon atom here, we can see that it is bonded to 1, 2, 3 and other carbon atoms in the graphene. Graphene is consist of 2-dimensional hexagonal carbon rings. It's clearly shown in this image, and it's a honeycomb appearance. Due to its structure and its bonding, it's a high electrical and thermal conductivity. The graphene have high electrical and thermal conductivity. Then what about its free electrons? There are some free electrons in the structure of graphene. So due to these free electrons, we can conclude its electrical and thermal conductivity. Okay. Then we will discuss about its cousin allotrope, or it's a similar allotrope, graphite. What is a graphite? Graphite has a layered structure with each layer arranged above the other. There is no covalent bonding between the layers of graphite. So the force of attraction between these layers are weak. So, and from these properties, we can conclude that it does not conduct electricity, but it can be used as lubricant. It is used as lubricant. And we move on to the next category. So up to this, we will discuss about diamond and its properties, graphene, graphite, and the last crystalline allotrope, fullerene. Fullerenes are some funny or some interesting structure. Just look at this picture and look at this picture. Do you see this building or this image in any way? It's like a sausage ball. Okay. The first fullerene was invented, or fullerenes are an interesting family of carbon allotropes. The first fullerene was uh, shown in this diagram. Okay, this diagram. This name was after Richard Buckminster Fuller. He did not synthesize the first fullerene, but was an author, inventor, and architect. He designed the geodesic domes that's shown in this picture. There are some dome-shaped buildings which look much like half of the saucer bar. For this reason, when fullerenes were the first synthesized and structure was identified to pretty much like a saucer bar. This architect's name was chosen for this new class of carbon allotropes, the fullerene. Fullerenes have a hollow spherical structure consisting of pentagons and hexagons. There are two categories included in these fullerenes. They are the hollow spherical structure is called a buckyballs, like this, and fullerenes with a cylindrical structure are used as a carbon nanotubes. They are called bucky tubes, that's shown in this picture. So there are two types of fullerenes. They are buckyballs and bucky tubes. And just discuss this uses. Fullerenes are used in medical field, and altered fullerenes are used in MRI imaging and in X-rays. Because of its structure nanotubes, they are excellent electrical and thermal conductor. They have made an evolutionary impact on the field of information and communication strategies. Okay, so we come the end of this lesson. We discuss about the allotropes of carbon, mainly the crystalline allotropes of carbon. Okay, let's conclude the topic by the carbon crystalline allotropes and amorphous allotropes. There are two categories. We learn what is crystalline carbon allotropes and a classification system for them, although that classification system is not shown here. We saw in this diamond, each carbon atoms are bonded in 4 other carbon atoms by a single bond, and that in the remaining allotropes. Look at these pictures. Each carbon atom is bonded to 3 other carbon atoms, and there is a mixture of single and double bonds. We learned that diamond forms a network 3D array of carbon atoms, that graphene is composed of layers of carbon atoms, while graphite stacked layers of carbon atoms. So at last the fullerene molecules are large, like cage-like molecules, and the nanotubes are essentially rolled up sheets of graphene. Okay, the main properties we investigated were hardness for diamonds. Okay, just look, hardness for diamond, slipperiness for graphene, graphite, and fullerenes. Good to excellent conducting abilities of graphene, graphite, and fullerenes. The high strength of carbon nanotubes. So the next time you see a pencil, remember that you are sliding off onto the paper a thin layer of graphite, and remind yourself of carbon allotropes and their many interesting properties and uses. So if you have any doubts, please comment down, and thank you for watching this video.